Good evening, everyone. Welcome to NPTEL tutorial session for the course Essentials of Oxidation Reduction and CC Bond Formation Applications in Organic Synthesis, taken by Professor Yashwant D. Vankar, retired from Chemistry Department, IIT Kanpur, and myself, Sri Lakshmi S. I am a PhD scholar in working in Chemistry Department in IIT Bombay. So this is our second tutorial session, and in the first tutorial session we have mainly discussed some assignment week 0 assignment problems as well as a summary of the week 1 lecture contents. Week 1 lecture contents. So today in this tutorial session we will be having a discussion on mainly the week 2 lecture contents. Firstly, we will start with the discussion of some problems related to the topics. Then we will go to the discussion on week 2 lecture contents, and if time permits we will try to solve some more questions in today's session. Okay, so before starting today's session, we will just quickly go through what we discussed in the last session. So, firstly, we have discussed this week 0 assignment questions with the mechanisms of all the reactions. So around 8 questions were there, and we have seen and discussed all the questions with the answers. Then we had a discussion about the week 1 lecture contents, where the lecture 1 was basically an introduction about the scores and introduction about the organic synthesis reaction and various molecules like natural products and other molecules related in organic synthesis. Then we have seen what is a synthesis, what are the reagents or different reaction conditions need to be used for carrying out a particular reactions, and what are those reagents, reactions and synthons, and how we can classify the selectivity of organic reactions like chemoselectivity, regioselectivity, stereoselectivity, then enantioselectivity, diastereoselectivity, which is a subclass of the stereoselectivity. And we have also discussed what is the basic difference between enantiomers and diastereomers. And okay, then in the lecture 2, in last class, we discussed about swan oxidation and related oxidation like Moffat-Fitzner oxidation, then how different groups have modified this oxidation condition and made it useful. All this oxidation like swan oxidation, Moffat-Fitzner oxidation, Barton oxidation, all are having similar mechanisms. We have seen the detailed mechanisms of all these reactions and how one is advantageous over the other. Like in Moffat-Fitzner oxidation, we have seen that the byproduct is dicyclohexylurea. So during purification, it is difficult to remove the byproduct. So swan oxidation is basically preferred over this Moffat-Fitzner oxidation. And then we have seen similar other oxidation like Kornblum oxidation, then Torsel oxidation, then Korekim oxidation, and how in swan oxidation reaction condition temperature plays an important role, like maintaining the temperature at minus 78 degrees celsius is very crucial in swan oxidation reaction, otherwise the side reaction through pumeral rearrangement can take place. Then we have seen what is pumeral rearrangement and its modification for the seleno pumeral rearrangement, and then we have seen several synthetic application of these reagents using DMSO BF3 thread combination to open the epoxides to get this alpha hydroxy ketones. And then we have discussed about the sulfoxides and selenoxides and how the sulfoxides and selenoxides can be utilized to produce alkenes, to form alkenes by undergoing a syn elimination reaction. Yeah, so that was the discussion in last class. We have solved several problems also, and we have seen the week one lecture contents. So, some of you have asked me about the books and references which you can follow for this particular course. So, some are given here, which are Organic Synthesis by M.B. Smith, third edition. Then, some Modern Methods of Organic Synthesis by W. Carruthers and call them fourth edition. Then Classics in Total Synthesis by Casey Nicola parts 1, 2 and 3. Then Organic Chemistry by J. Clayton and Modern Organic Synthesis by G.S. Wiefel and M.H. Nance. Then of course you can follow the literature reference which are being published from the earlier time regarding all of the reactions. So, before going to the discussion on week 2 lecture contents, firstly, we will discuss some problems regarding these topics, and some of them are not related to these topics. We will discuss those also. So, the first question is identify the major product A in the following transformation. So, this particular diol is there, and here two diols are protected with this protected as acetonide, and this is treated with this combination of DCC, DMSO, pyridine, trifluoroacetic acid in benzene solvent. So which of these four compounds can be formed here? So which would be A? And we have already seen last class also and now also which reaction it is, and this is a named reaction, how it is proceeding, and which would be the correct answer. So, as we have discussed, this is an example for Fitzner-Moffat oxidation, and the correct answer is option C. So, this diol is getting oxidized to this ketone, alpha beta unsaturated ketone. So, basically, one of that is getting oxidized to ketone, and other one is undergoing elimination to form that alpha beta unsaturated ketone. We will see how this works basically. So, I think we have already discussed this mechanism, Fitzner-Moffat oxidation. Maybe I will go to that. That will be better. Yes. So here it is. So we are using the combination of DMSO, DCC, and pyridine. Or here they are using this H3PO4. So mechanism is almost similar. Yeah, so first what is happening, this pyridine and DCC will react to form this activated species, that is this nitrogen lone pairs of this DCC will take up this a proton from this protonated pyridine and it will form this intermediate. Then this DMSO oxygen will attack over this carbon and this double bond will shift over this nitrogen to stabilize the positive charge on nitrogen and form this intermediate. Then this oxygen lone pairs, which is our starting material, will attack over this uh, sulfur and it will form this intermediate. Again this pyridine will take up the proton from this, so we have seen the mechanism is intermolecular, so it will take the proton from this pyridine and this bond will migrate over the sulfur and this will break and this will eliminate to form this intermediate. Again one proton loss which is taken up by this nitrogen of this DCC will form this intermediate. Then the CH2 will take this proton and it will form this aldehyde. So this is the basic mechanism for oxidation. So what is happening, one of that is getting oxidized and other one is going undergoing elimination to form that alpha beta unsaturated ketone. Moving on to the next question, the intermediate involved in the given etard reaction is. So we have not discussed etard reaction in any of the lectures, but I thought since it is related reaction, we can discuss this mechanism as well. So here we have taken toluene, and toluene is converted into benzaldehyde directly. So here it is not the conversion of an alcohol into an aldehyde. Directly a methyl group on aromatic ring is converted into an aldehyde group, and they are using the CrO2Cl2 as a reagent. So using the CrO2Cl2 reagent, how we can make convert this toluene into this benzaldehyde, and you have to identify which intermediate can help in this transformation. Okay, so here what is happening? This is a TAD reaction. So, firstly, from this toluene, this proton will be taken up by one of the oxygen of the CrO2 Cl2, and this bond will shift over here, and then this aromatic ring, this carbon will attack over this chromium and form this intermediate. So, this is the in reaction. And then what is happening again? This another oxygen, another Cr double bond O is there. That oxygen will attack over this one, and then this will shift over here, and this will migrate over this chromium and form this intermediate. So this is an example for 2,3 sigmatropic rearrangement. Then what will happen? Again, the Cl minus, which will eliminate from this, will take this proton, and this bond will shift over here, and this will eliminate, so resulting in the formation of this benzaldehyde. So out of this, the correct answer would be which one? Yes, the correct answer would be option 4, that is given here. So in a TAD reaction, the first step is in reaction, and the second step is a 2,3 sigma tropic rearrangement. Moving on to the next question, the major product formed in the following reaction is. So here, this bridge system we are taking, and in the first step we are treating with three reagents: first magnesium, then carbon dioxide, and then hydrolysis condition. Then in the second step we are treating it with this oxalyl chloride, and in the third step with triethylamine. So out of these four options given here, which can be the major product? So here what is happening, first magnesium will convert this bromide into the corresponding Grignard reagent, that is Br will be converted into MgBr. Then to this carbon dioxide will attack and hydrolysis will result in this formation of this carboxylic acid. Then, in the presence of this oxyl chloride, this carboxylic acid will be converted into this corresponding acid chloride. Then, what will happen? Triethylamine will take the proton from the alpha position of this acid chloride, and this will shift over here. And when it come back, this chloride will leave, and this will form this ketene kind of intermediate. Then, to this ketene, this 2 plus 2 cycloaddition we can say. So this double bond and this double bond will undergo a 2 plus 2 cycloaddition reaction to form this compound. So this is not generally related to this oxidation reaction, but since this similar reagents we are using here like oxyl chloride, I thought of keeping it here. And you can go through this mechanism. I hope it's clear. Firstly, Grignard reagent formation, then carboxylic acid, and then carboxylic acid will get activated into acid chloride, and then triethylamine will make the acid chloride into that corresponding ketene. Then 2 plus 2 cycloaddition will take place to give that compound. And here the correct answer would be then option 4. So here one this double bond is missing. Moving on to the next question, identify the major product in the following transformation. So, this particular compound in two steps, first treating with this potassium hydroxide and the second step treating with chromium trioxide, which can be the major product. So, four options are given here. What can happen in the first step and what can happen in the second step. So here what is happening first in the presence of this potassium hydroxide, this acetate group get hydrolyzed and it will be converted into corresponding alcohol. Then in the presence of this chromium trioxide, that alcohol will get oxidized into ketone, and in the same step this bond will migrate over here and form an alpha beta unsaturated ketone which is more stable. So the correct answer here would be option B, and similar reaction sequence is given here. So here from here if we see this KOH is hydrolyzing this acetate to form this OH, and in the presence of this chromium trioxide in pyridine, this double bond is shifting over to here and this OH is converted into this ketone to give this progesterone. So here this chromium trioxide pyridine condition is there, so that's why I kept this example. Now, moving on to the next question, identify the right sequence of reagents that will result in the transformation given below. So here, what has happened is both of this pivotal group got deprotected in the product, and this alcohol is converted into an alkene. So what can happen here? So the four options are here. First one is methylbutyl diballage, then SO3 pyridine DMSO oxidation. Second option is first diballage, then SO3 pyridine DMSO oxidation, then methylbutyl. Third option is first oxidation, then methylbutyl, then diballage reduction. And last option is first diballage reduction, then methylbutyl, and last oxidation. So out of these four options, which combination of or which sequence of reactions and reagents can give this pivotal protection of both the pivotal group and this conversion of this hydroxyl group into the corresponding alkene? So here the correct answer is first this oxidation, then we will be doing this methyl-butadiene olefination and followed by this dibalage reduction. So as we can see the sequence of reaction involved here. So this is the compound which we have taken. So firstly this SO3 pyridine DMSO oxidation will oxidize this free hydroxyl group into this aldehyde. Then followed by treating this aldehyde with this methyl-butyric, we will get this alkene, and then dibalage reduction will deprotect this both the pivylyl group which are esters. So basically it will reduce the esters to form this alcohol. So that's how we will get this reagent. So the correct order of reaction will be oxidation, then methyl-butyric, and then this dibalage reduction. Moving on to the next question, identify the major product formed in the reaction given below. So here this compound is treated with first with this BH3-DMS and then with this H2O2 NaOH. This is also a very well-known reaction. So which reaction or which product can form under this condition? So here this is an example for hydroboration oxidation reaction. So what will happen is, firstly this alkene will coordinate, this boron will attack this alkene and it will form this intermediate, and then again this boron can coordinate with this oxygen also, so that will give this intermediate. Then this proton transfer will occur to this position and it will stabilize the positive charge on oxygen, and upon treating with H2O2 NO2 NaOH, this borane will be replaced with the hydroxyl group, so we will be getting this corresponding diode. So this is an example for hydroboration oxidation reaction, and in the same pot this ketone is also getting reduced. Now the next question, which of the following reagents, how many more questions are there? Two, three, okay, three more question, and then we will go to the discussion of last week lectures. So which of the following reagents would carry out the following transformation? So what is happening here, this ester, this acid group is somehow converting into this carbonyl group, and that is attacking over the center. So which of the reagent combination, or the correct, which of the correct sequence of the reagent combination can give this reaction? So first option is diisomethane, then swan oxidation, and then rhodium acetate. Diisomethane, then oxyl chloride and rhodium acetate. Then second one is diisomethane, rhodium acetate, and then oxyl chloride. Third option is oxyl chloride, then diisomethane, and then rhodium acetate. And fourth option is oxyl chloride, rhodium acetate, and then diisomethane. So which would be the correct sequence of reaction? So here the correct combination of reagents is first this oxyl chloride, then diisomethane and rhodium acetate. So what is happening here is first oxyl chloride will convert this carboxylic acid into this acid chloride, and then diisomethane will convert this acid chloride into the corresponding this diiso compound, and rhodium acetate will undergo insertion over this diiso compound to form this carbene type of intermediate, and that will attack over this center to form this compound. So the correct answer would be option C. Moving on to the next question, identify the major product A in the following transformation. So this particular compound upon treatment with this N-iodosuccinimide and this vinyl ether kind of derivative, which will be the major product we can get here. So here what is happening, the correct answer is option A. And what will happen, so this is the compound. So with this iodonium NIS, first this iodonium ion formation will take place over this, and then this oxygen lone pairs will fall over that, and that iodonium ion will open to form this particular intermediate. Then this, so this is the intermediate that will be formed. Here iodine will be there, and here OET will be there with a positive charge on this oxygen. Then this oxygen lone pairs will attack over this center, and this will come over here to form this compound. So the correct option here is option A. This last question, and then we will move on to the discussion of week 2 lectures. So the question is, identify the major product A in the two-step reaction sequence given below. So the first step is, first reaction is thionyl chloride and diethyl ether, and in the second step treating with methanol, what can happen? So this is a very simple reaction. So here what will happen first, as we said earlier, this thionyl chloride will convert this acid into acid chloride also, and this alcohol into corresponding this sulfoxide, we can say. Then what is happening, SO2 elimination, this sulfur will attack over the center, this will come over here, this will come over here, and when this go back, the Cl will leave and it will form this kind of intermediate. Then again, under methanol condition, the Cl minus will attack over the center, and this will open, stabilizing the positive charge on sulfur. And in that step itself, this acid chloride is getting converted into this corresponding ester in the presence of this methanol. So we will be getting this corresponding product. Okay, now we will move on to the week 2 lecture content. So here we have given some of the recap of the previous class which we have already discussed, like selenium oxide elimination to give this alkene. So first, this one for addition using this phenyl Gilman reagent, so it will give this phenyl over here, then phenyl selenium bromide quenching with phenyl selenium bromide will give SEPH over here, and then H2O2 will give this selenium oxide, and at then elimination will also happen to form this compound. So it is happening like this, that sin elimination is taking place. So the same can happen with sulfoxide. So for sulfoxides it needs higher temperature, but with selenoxides it can happen at lower temperatures also. Then we have seen this what can happen if we are using doing swan oxidation at this higher temperature or. Hello? That only. Yeah, that only I saw. Which one you want? BBA3. Yeah, yeah, Blackish it used to do that. Anisha used to use, I don't know about that. But in that only we used to keep all catalysts. Okay. I was saying, in it was a building well for catalysts. Yeah. You asking the right when you say catalyst. Okay, so at this elevated temperatures, it can undergo this pumerar rearrangement as well, and then we have seen the selenopumerar followed by selenoxide eliminations. So moving on to the last week lecture contents now. So firstly, we have seen in the lecture 5 oxidations using organoselenium compounds and SeO2. So there we have also seen the methods to make organoselenium compounds, like from different aromatic alkynes, how we can prepare this organoselenium compound and this ketones or haloketones, how this organoselenium compounds can be made. Then we have seen some synthetic utilities of this selenium compounds, where this elimination can happen and then it can undergo again this isomerization to give this type of compounds, and then how this type of very active compounds can be made. And another synthetic application was the installation of the double bond over here, and then LDA and this formaldehyde to introduce this CH2OH over this center, and then reduction of this double bond will give this rejoin stereoselective hydroxymethylation. Then oxidations with SeO2. So we have seen here set of rules for the oxidation with SeO2. First one was oxidation at the allylic and benzylic position using SeO2, and oxidation of ketones to 1,2-diones using SeO2. For the oxidation at the allylic and benzylic positions using SeO2, we have seen several rules to predict the regiochemistry during SeO2 mediated allylic hydroxylation. So the first rule was that the oxidation always occurs at the disubstituted side of the double bond, like here, provided there is a non-bridged alkynyl hydrogen is available. So here non-bridged alkynyl hydrogen is available, so it will prefer this position over this position. Now the second rule was oxidation of one alkyl cyclohexene occurs in the ring rather than in the side chain, and oxidation never occurs at the bridge head position because it will not favor this type of intermediate. Then the preferred order of reactivity is expected to be secondary, then methyl, then tertiary. And then the fifth rule was a diene rather than a tertiary alcohol is expected to result in the case of preferred position is tertiary. So rather than favoring this kind of compound, it would be favoring this kind of diene by an elimination sequence. Then in such reactions, we can also observe an allylic rearrangement. So here this double bond position, as we can see, allylic oxidation is taking place at this center and this double bond is migrating to this center. So we are getting this allylic rearranged product. Then the next rule is if there are two similar preferred positions on both sides of the alkene, both positions are oxidized. So here both positions are preferred, so this position is also oxidized and this position is also oxidized. And then we have seen several examples as well as mechanisms related to this SeO2 TBHP mediated oxidation. So basically, what is happening? Firstly, this oxygen will take this proton and an in reaction will take place. This will shift over here and this double bond will attack over the selenium to form this chair type of transition state. Then that will give this elimination of this water molecule will give this intermediate. Then again this OH will attack over this center, double bond will come over here and this will eliminate, and in workup it will go to give this allylic alcohol. Then the second reaction was oxidation of ketones using 1,2-diones using SeO2. And here we have seen two mechanisms like Corey's mechanisms and Sharpless mechanisms. So in Corey's mechanism, what is happening? This ketone, we can tautomerize it and make it in the enol form, and that undergo react with SeO2. So this oxygen will attack over the selenium to form this intermediate. Then this oxygen will attack over this double bond. This will come over here and this will go like this. Sigma tropic rearrangement will take place, and then this will come over here and this will eliminate to form this diketone. So this is the mechanism suggested by Corey's group. Then another mechanism which is similar to that but little modified, that is suggested by the Sharpless. So here what is happening in this enol form, firstly this SeO2 is attacking over this double bond. So this double bond will attack over the selenium to form this intermediate, then proton loss and this water OH loss to form this intermediate. Then what will happen? This water molecule will attack over this center and then this will come over here and this will eliminate to form this diketone. So, in comparison with Corey's intermediate, we can see it is like this is Corey's intermediate and this is Sharpless intermediate. So, both will give us the same product. Then in the next lecture, we have seen the sulfoxide sulfinate rearrangement, which is also known as Mislow-Evans rearrangement, which is a concerted process and it is a 2,3 sigmatropic rearrangement. So using this kind of reaction, we can generate allyl sulfoxide, which is a vinyl anion equivalent. So what is happening? This allyl sulfoxides is converted into this allyl sulfinate ester, and using a thiophile this bond is cleaved to get this alcohol, allylic alcohol type of compounds. So the thiophiles used here can be this trimethoxyphosphine diethylamine or this amine derivatives. So this is how it happens. We will see the mechanism. So firstly what will happen, this sulfoxide, either it can exist in this form as well and then thiophile, and or we can quench it with a R plus and it can give this intermediate, then same thing can happen to give this. So if we are quenching this with an R group R plus, it will give this, or in this way also it can give this intermediate. So it is an anion of allyl sulfoxide is a vinyl anion equivalent. Then we have seen some synthetic utility for this reaction and how this transition state is favored and how this stereochemistry is retained in this reaction. Then this role of a thiophile, that is here this trimethoxyphosphine is used to cleave this oxygen sulfur bond. So first this oxygen sulfur bond is cleaved and this O minus will take this proton from this methanol to form this, and this is the byproduct which we are getting, which can again undergo this O minus can attack over this phosphorus to form this intermediate, and this will be the two byproducts. So similarly, like this trimethoxyphosphine, this amine derivatives can also be used to cleave the oxygen SPH bond. Then these are some of the synthetic applications. Then we have also seen the sequential 2,3 sigmatropic rearrangement and seen elimination of allyl sulfinate to convert this allylic alcohol into 1,3 dienes kind of system. So here what is happening, first this OS aromatic ring will form, and then that is undergoing a 2,3 sigmatropic rearrangement to get this. Then a thiophile can give this product by elimination. So similarly, this could be converted into this one, and this could be converted into this compound. Then we have seen in the lecture 7, we have seen the selenoetherification reaction, which is an advanced intermediate in the synthesis of natural products like milbemycin, avermectin. Then after this selenoetherification reaction, we have seen this remote oxidation using sigmatropic rearrangement and Pumara reaction as well, and some examples for that. Then the next reaction which we have seen is segusite oxidation and 1,2-diketone and enone transpositions. So in the segusite oxidation, basically what is happening in the presence of palladium acetate and a co-oxidant like benzoquinone, we are converting this type of compound in all silyl compounds into an alpha beta unsaturated ketone. So the mechanism goes like this. Firstly, the palladium will coordinate with this double bond, and then transmetallation will take place to form this oxoallyl palladium complex. Then beta hydride elimination will give rise to this intermediate, and which upon this workup or removal of this one, we will be getting this compound, and whatever palladium zero will be formed, that will be oxidized back into this palladium 2 oxidation state by the co-oxidant used here, that is benzoquinone. So that was the segusite oxidation. Then we have seen several examples using other co-oxidants like oxone, which is a mixture of this potassium sulfates. And then we have seen the how these ketones can undergo like how we can make this alpha beta unsaturated ketones by other methods from this alpha haloketones. But here one of the problem which we can face is the type of Tversky type reaction. Ring contraction can take place in the case of alpha haloketones. So more than this method, preferred one is segusite oxidation. Then another method is treating with LDA and then phenyl selenium chloride and then elimination to give this type of compounds. So these are the different ways to make this alpha beta unsaturated ketones from ketone. So we have also seen the application of saggusite oxidation in the total synthesis of different natural products like morphine and peribicin. Then other than oxone and benzoquinone, even oxygen is also used to oxidize the palladium zero species into palladium 2. Then in the lecture 9, we have seen the 1,2 ketone transposition using this Shapiro type of reaction. So firstly, this is converted into the stosyl hydrazine, then butyl lithium. First equivalent will abstract proton from here, and next equivalent will abstract proton from this nitrogen to form this intermediate. Then treating with this disulfides, we will be getting this compound, and then again butyl lithium will abstract proton from this center, and then this docile elimination will give this intermediate, and again then N2 elimination will give this intermediate, and then workup will give this one. And here then for removing this thionyl group, we are using this HgCl2 or TiCl4 usually to convert this type of compound into this ketone. So here water molecule is playing the role, that's why we are using this aqueous acetonitrile reagent. So TiCl4 is another way to remove this. So here also we can see this ketone was initially here and now in the product it is here. So this is also an example for 1,2 ketone transposition. Then we have seen this Doben-Mignon rearrangement, which is 1,3 enone transposition, similar to that, but here we are using this firstly some nucleophile we are attaching, and then PCC oxidation will give this type of intermediate, this type of compound. So this is 1,3 enone transposition. So here what is happening, firstly it will coordinate with this OH will attack over this chromium trioxide to form this intermediate, and then this sigmatropic rearrangement will take place to form this, then this will go and give this alpha beta unsaturated ketone. Then this is an example for that. And in the last lecture we have seen this Martin pyridine in oxidation. So it is used for the conversion of alcohols into aldehyde, and this is an hypervalent iodine reagent with 12 electrons and 5 bonds attached to iodine. So here the peculiarities of Martin pyridine reagent are, so this reagent was developed by DB Des and JC Martin in 1983, and it's having neutral pH and room temperature oxidations can be carried out in short reaction times of 30 minutes to 2 hours. Then workup is also simple. Sometimes we just have to do filtration and then directly concentrate and do column. And the chemoselectivity is high. Benzylic and allylic alcohol are oxidized faster than saturated alcohol. Then it is having a high tolerance to sensitive functional groups like furans, sulfides, vinyl ethers. And N-protected amino alcohols can be oxidized even without epimerization. And because this epimerization occurs with other oxidizing agents like Swan oxidation, and the DMP reagent DMP reagent shelf life is also quite long, so storage is also not an issue. Usually, we say like DMP, if we are storing more time, it used to be more active than the freshly prepared DMP. Then we have seen how it is prepared. So using this iodobenzoic acid and oxone in water will give this intermediate. Then treating with this PTSA and acetic anhydride will give this desmartin periodinate. So this is also an oxidizing agent, which is iodoxybenzoic acid, and then its acetate equivalent, that is desmartin iodine, is also oxidizing agent. So this is oxone, potassium peroxymonosulfate, potassium caroate, potassium hydrogen sulfate, potassium sulfate. So the careful things we have to keep in mind is IBX and KBRO3 both are explosive, especially this KBRO3. So oxone method is more preferred over this KBRO3 method. Then this mechanism, so different mechanisms are possible either through the 7-member transition state or 5-member transition state, or through this intermolecular fashion. Then we have seen how the steric effects play a role in the mechanism of the reaction, and how steric factors can control the rate of the reaction. Then we have also seen some examples using DMP for oxidizing alcohol where this one oxidations was problematic. Yeah, so that was it. So up to there, we have seen this in the last week lecture contents. I hope it is clear. If you have any doubts or question regarding the problems discussed today or regarding the week 2 lecture contents, please feel free to ask. I hope you enjoyed today's session, and I hope it was helpful for you. Thank you for listening and thank you for joining. See you in the next tutorial session, which would be on the coming Saturday. So thank you so much.